In October 2018, a storm hit two American islands so violently that it stripped the vegetation off their hillsides in a single afternoon. It was called U2. For 6 years, it stood as the strongest typhoon ever recorded near the Mariana Islands. That record didn't survive the year 2026, because in April, a storm called Sinlaku broke it. And now, less than 90 days later, a second Category 5 system is bearing down on the exact same chain of U.S. territory, with peak winds that may exceed both of them. By the end of this video, you'll understand why meteorologists are calling this a once-in-a-generation coincidence of geography and physics, and why the real danger isn't the number on the wind gauge, but something happening underwater, 300 feet below the surface, that most people watching the news will never hear explained. This is the story of Super Typhoon Bavi. Let's start with what actually happened, because the numbers alone don't tell you much. Bavi was a disorganized tropical storm on July 2nd, drifting west at a lazy 15 miles an hour with winds of just 60 miles an hour. Unremarkable. The kind of system that barely makes the news. Then, over the next 36 hours, something changed. Its winds jumped by 100 miles an hour. Not over a week, not over a few days, in a day and a half. That easily exceeded the official meteorological threshold for rapid intensification, a 35 mile an hour increase in 24 hours. Bavi didn't just cross that threshold, it nearly tripled it. But here's the question that actually matters. Why? The answer isn't in the atmosphere, it's underneath it. Tropical cyclones are heat engines. They pull warm, moist air upward, release that heat as the moisture condenses into clouds, and use the pressure difference to spin faster. The fuel for that engine is warm ocean water, and specifically, warm water that runs deep, not just at the surface. A shallow layer of warm water gets churned up and cooled within hours by a storm's own winds. That usually puts a natural brake on intensification. But when the warm layer extends far below the surface, what scientists call high ocean heat content, the storm can't cool its own fuel source. It just keeps feeding. The waters Bavi crossed were sitting around 29 to 30 degrees Celsius, roughly 84 to 86 degrees Fahrenheit, and that heat extended deep. Combine that with something else, unusually low vertical wind shear, meaning almost nothing in the upper atmosphere was tilting the storm off balance. Take away the turbulence, add unlimited fuel. That's how a system goes from disorganized to Category 5 in a day and a half. But that isn't the strangest part. Right now, hundreds of miles away, something invisible is happening inside Bavi's own core. A process that could either save the Mariana Islands from the absolute worst-case scenario or make it dramatically worse. It's called an Eyewall replacement cycle, and to understand it, picture the eye of a hurricane not as a hole, but as a spinning wall of the most violent wind on the planet, wrapped tight around a calm center. As a storm intensifies past a certain point, that wall becomes almost too efficient. A second wall of thunderstorms forms outside it, like a second skin. The two compete for the storm's energy. Eventually, the outer wall chokes off the inner one, contracts, and becomes the new eye. Satellite analysis put the odds of this process already underway in Bavi at roughly 64% as of Saturday, July 4th. Here's why that matters more than the headline wind speed. During the transition, the storm typically weakens slightly. Its peak winds drop for a period of hours. But the wind field around the center often expands dramatically. Forecasters expected the storm to grow significantly larger during this cycle, spreading dangerous conditions across a wider stretch of ocean than before. A smaller, more intense eye threatens one island directly. A larger eye that has just finished rebuilding itself threatens several islands at once, which is exactly the geography Bavi was approaching. This is not speculation. This is standard, well-documented storm physics. What remains genuinely uncertain, and forecasters were honest about this, is the timing. If the cycle finishes before Bavi reaches the islands, re-strengthening could push the storm back toward its highest intensity right at landfall. Forecasters noted that if the replacement cycle completed quickly, renewed intensification to at least 173 miles per hour was possible as Bavi neared the Marianas. If it doesn't finish in time, the islands could catch the storm mid-transition, slightly weaker winds but spread across a much wider area. Either way, the same conclusion holds. The National Weather Service in Guam had already warned of sustained winds up to 175 miles an hour, with gusts to 210. That's not a forecast anyone treats lightly. When history refuses to stay in the past. To understand why residents of these islands were filling water jugs and taping windows for the second time this year, you need to go back to April. Super Typhoon Sinlaku peaked at 185 miles an hour on April 12th, southeast of Guam, at the time the strongest tropical cyclone to make landfall anywhere on Earth in 2026. It came ashore over Saipan and Tinian as a Category 4 storm with 145 mile an hour winds, killing 17 people and causing an estimated $1.5 billion in damage. Here's the statistic that should stop you. Sinlaku was the 10th Category 4 or 5 tropical cyclone to strike a U.S. state or territory in the past decade, matching the total number of such landfalls the entire country experienced in the previous 57 years combined. 1 decade. As many catastrophic landfalls as the previous 6. Now, 3 months later, Bavi is following what officials describe as a track that echoes Sinlaku's almost exactly, moving in from the east, aimed squarely at the same small cluster of islands. There is one meaningful difference. Sinlaku curved north after landfall and lingered, dragging its rainfall over the islands for an extended period. Bavi's forecast track keeps it moving steadily west-northwest, which, if it holds, means less time spent stalled directly overhead. That's a difference in duration, not in intensity. And it's the kind of distinction storm scientists care about deeply, even when it sounds like a technicality to everyone else. What happened next surprised even people who'd lived through typhoons their whole lives. Recovery from Sinlaku was still incomplete. The American Red Cross reported that some residents remained in temporary shelters or under makeshift roofs as Bavi approached. A hospital that had flooded in April was still working through repairs. Families who had just replaced a roof were buying plywood again. One resident put it simply, 2 super typhoons in 2 months in the same year was something the Marianas had never seen before. That's not internet hyperbole. That's a description of an actual, measurable pattern, and it connects to something larger happening across the entire Pacific Basin. The world's oceans just recorded their hottest June on record, according to the EU's Copernicus Marine Service, with the potential to set new highs in the months ahead. Warmer oceans don't create typhoons out of nothing, but they do raise the ceiling on how much fuel is available once a storm forms, precisely the mechanism that turned Bavi from a Tuesday afternoon tropical storm into a Category 5 system within 72 hours. Correlation isn't causation, and no single storm can be attributed to ocean warming alone. But the broader trend, more high heat content water, more storms capable of extreme rapid intensification, is one scientists have been tracking for years, not weeks. So where does this actually go? Today and tomorrow, known, high confidence. As of Saturday afternoon local time, Bavi was roughly 390 miles east of Guam, 370 miles east-southeast of Rota, moving west at a crawling 8 miles an hour with sustained winds of 165 miles an hour. JTWC's closest approach estimate placed the core nearest Saipan and Rota around 2200 UTC on July 5th. The most recent track shift had nudged the projected path slightly south, threading between Rota and Tinian, with Rota nearest the center, though officials were explicit that this could still move north toward Saipan or south toward Guam. But that isn't the full picture, because a track line on a map doesn't capture how wide the danger zone actually is. 48 hours. Probable, moderate to high confidence. Tropical storm force winds were expected to arrive Sunday evening, with full typhoon force winds moving through from Monday morning into early afternoon local time. Rainfall estimates ranged from 12 to 20 inches, raising serious flash flood risk across Guam and the wider Marianas. Wave heights were forecast to build toward 25 to 35 feet, with the potential to reach 45 feet in open water. Next week, probable, lower confidence on details. Once Bavi clears the islands, the steering pattern that guided it here isn't expected to change. Global model consensus placed the most likely subsequent track toward Taiwan or eastern China by around July 10th. That's 5 days out, enough time for meaningful shifts, but the general westward trajectory has held steady across multiple forecast cycles. Long term, speculative. Whether Bavi weakens rapidly after landfall interaction, re-intensifies over the Philippine Sea, or curves depends on atmospheric patterns that are still forming. This is the honest edge of forecasting, the point where confidence drops and uncertainty is the correct answer. Here's where the internet gets it wrong, and it's worth pausing on why. Misconception 1. Category 5 means the entire island gets flattened. It doesn't work that way. The most extreme winds are concentrated in a ring just outside the eye, often only a few miles wide. A shift of 20 or 30 miles in the track can mean the difference between a direct hit and a serious but survivable brush with the outer bands. People assume a single number describes the whole storm. It describes the peak, not the footprint. Misconception 2. Because Sinlaku already hit, this storm can't be as bad. There's no such thing as a typhoon quota. Ocean heat content resets with each storm's track. Two systems taking slightly different paths can each find abundant fuel independently. The idea that one storm uses up the danger is understandable, but it isn't how tropical thermodynamics works. Misconception 3. The Eyewall replacement cycle means the storm is falling apart. It's the opposite of collapse. It's restructuring. A storm mid-cycle can look temporarily weaker on a wind gauge while becoming more dangerous in terms of the area it affects. Calling it weakening without the context is technically true and practically misleading. While residents board up windows, a separate, quieter form of vigilance is happening across satellite feeds and reconnaissance data. Forecasters are watching central pressure, which had dropped to around 920 millibars by Saturday, according to the Japan Meteorological Agency, a figure that drops further as a storm strengthens. They're watching eye diameter and symmetry on infrared satellite, tracking whether the eyewall replacement completes cleanly or drags out. They're watching upper-level outflow, specifically whether enhanced outflow developing near Japan connects with the storm and fuels another intensification burst. They're watching wind shear forecasts for the days after landfall, since increasing shear was expected to eventually erode the storm on its approach toward Asia. And on the ground, emergency managers are watching something far less glamorous than satellite loops: fuel supply, shelter capacity, and how many buildings damaged in April are still standing at full strength. That last one might be the most important instrument of all. A structure weakened by one typhoon doesn't necessarily fail during the next, but engineers know that repeated stress lowers the threshold at which materials give way. CNMI's Disaster Response Office had already noted the storm was moving unusually slowly, drawing direct comparison to Sinlaku's sluggish pace through the same waters in April. And a slow-moving storm means more time for wind and rain to work on infrastructure that never fully recovered. Whether Bavi ultimately earns the informal label some meteorologists have floated, a Pacific megastorm, isn't something science can determine in advance. That designation, if it comes, depends on how long the storm holds its peak intensity, whether it strikes population centers directly, and the scale of damage once the winds finally die down. So go back to the question this video opened with. Why does a storm chasing a 6-year-old wind speed record, following almost the exact path of a typhoon from 3 months earlier, actually matter? Not because of the number on the anemometer. Numbers like that are dramatic, but they're not the whole story. It matters because of what's underneath the water. Heat, stored deep, feeding an engine faster than most forecasters have seen. It matters because of what's happening invisibly inside the storm's own core, a structural cycle that could expand its reach even as its peak winds briefly ease. And it matters because of what's sitting on those islands right now. Roofs rebuilt only weeks ago, a hospital still finishing repairs, communities that had barely put away the plywood from the last warning. Bavi isn't remarkable because it might become the strongest storm of the year. It's remarkable because it's a case study in how modern tropical cyclones are behaving, intensifying faster, restructuring in ways that widen their danger zone, and arriving in places that haven't finished recovering from the last one. The wind will die down within days. What the science reveals about why storms like this keep forming, that part doesn't end when the warning is lifted.